Great Nobel Prize winning physicist Richard Feynman was once asked to convey, in a single sentence, the most important scientific knowledge that humans possess. His answer was short and simple. Everything is made of atoms. Believe it or not, this was believed to be the case over 2,000 years ago in ancient Greece and India. However, it wasn't until the modern era that we were able to prove it to be so. Learn more about atoms and how we discovered they existed on this episode of Everything Everywhere Daily. Most of what the ancients knew about the physical world was wrong. Just flat out wrong. Aristotle, for instance, thought everything in the world was made out of just 4 elements: earth, air, fire, and water. According to him, everything consisted of some combination of those 4 elements. Almost every ancient culture had some ideas of how the world works, which doesn't really stand up to modern science. That being said, given the state of knowledge hundreds or thousands of years ago, you can't really blame them. Most of the ideas about the world were based on philosophy more than science. They had ideas that made sense to them, but weren't based on experimentation or even observation. However, there were a few cases where they basically got it right, even though they really didn't know it at the time. And this is the case with the theory of atoms. What we call science used to be part of philosophy. The branch of philosophy which dealt with the natural world was known as natural philosophy. One school of ancient natural philosophy was called atomism. There are 2 ancient civilizations that each independently developed theories of atomism: Greece and India. Around 600 BC, one of the Vedic schools of thought was known as Vaisheshika. It was developed by the Indian philosopher Kananda, and it postulated that the world could be reduced to invisible bits known as paramanu. According to the Vaisheshika school, everything was made up of paramanu, and everything in the world could be thought of as a combination of paramanu and the interactions between them. About 200 years later, the same idea was independently developed in Greece. A philosopher by the name of Democritus believed, like Kananda in India, that the world was made up of invisible particles, which he called atomos, which means uncuttable. According to Democritus, there were an infinite number of atoms of different sizes and shapes. They were always in motion, and the material's nature reflected the atom's nature. For example, water atoms would have been slippery. Iron atoms would be heavy with hooks that connected them together. Sweet things had smooth atoms, and bitter things had jagged atoms. Also, according to Democritus, between the atoms there was nothing, just a void. And atoms could also not be created nor destroyed. Both Democritus and Kananda simply used deductive reasoning to come to these conclusions. Aristotle did not believe in atomism. He thought his 4 elements could continuously be divided forever. Moreover, he didn't believe in a void, which was necessary if you believed in atoms. Despite having written 80 different works, none of the writings of Democritus survived. Everything we know about him is what was written about him by others. The works of Aristotle, however, did survive, and his ideas eventually took hold and were revived during the Middle Ages. Nonetheless, there was a rediscovery of atomism in the 13th century, and there were scientists who believed in atomism, including Isaac Newton. At this point, while modern science was still developing, believing in atoms was still pretty much a matter of philosophy. There wasn't any proof. Our modern-day understanding of atoms began to develop in the late 18th and early 19th centuries. There were discoveries being made on an almost regular basis about the fundamental elements. One of the first major steps towards figuring out atoms came from the French chemist Antoine Lavoisier, who postulated the law of conservation of mass. He realized that in any chemical reaction, the total mass before and after the reaction was the same. However, the big step in atomic theory came from the English chemist John Dalton. Dalton developed what is known as the law of multiple proportions, which stipulates that the masses in any compound were actually ratios of small whole numbers. He felt that each element, and there were new elements being discovered all the time, were their own unique atoms. This theory made perfect sense. It explained chemical equations, and it explained the discovery of elements. Through the 19th century, more evidence piled up consistent with the atomic theory of matter. Avogadro's law, the ideal gas law, and the discovery of Brownian motion, and everything else discovered during this period, gave continued support to the idea that everything is made of atoms. The idea that atoms were the smallest unit of matter actually fell apart in 1897, with the discovery of the electron by the British physicist J.J. Thomsen. He found that there had to be a negatively charged particle that had a mass 1,800 times less than hydrogen, which was the lightest known atom. Thomsen figured that his new particle was smaller than an atom and was actually a constituent part of an atom. With this new discovery, Thomsen created a new theory of the atom, which was dubbed the plum pudding theory. This theory held that there was a positively charged substance that the negatively charged electrons were embedded within, just like how raisins were embedded in plum pudding. Thomsen's plum pudding model didn't last very long and was disproven only a few years later. The New Zealand physicist Ernst Rutherford put the plum pudding model to rest when he discovered that atoms had a very small, dense nucleus. Rutherford had already won the Nobel Prize in 1908 for his work on radioactivity. In a famous 1911 experiment known as the gold foil experiment, he actually set out to prove Thomsen's atomic model. He fired alpha radiation particles at a thin piece of gold foil. He expected all the alpha particles to go right through. Instead, what happened is that some of the particles were reflected, oftentimes in very odd angles, including straight back. This result was unexpected and shouldn't have happened if the plum pudding model was true. Rutherford realized this could only have happened if two things were true. The first was that there was an extremely dense, positively charged nucleus to the atom that was reflecting some of the alpha particles back. And the second was that there was a whole bunch of nothing everywhere else allowing the particles to pass through. Rutherford proposed a new model of the atom where there was a small, dense, positively charged nucleus with small, negatively charged electrons which orbited about it like planets orbit the sun. While this model did fit the data better than the plum pudding model, it raised just as many questions. What kept the electrons in orbit, and what did the nucleus consist of? Just 2 years later, the Danish physicist Niels Bohr expanded on the model by explaining that electrons would have been parked at different levels depending on their energy. And that same year, in 1913, another discovery needed to be explained. The British radiochemist Frederick Soddy discovered that there were some atoms that had different weights, and these became known as isotopes. In 1919, Rutherford again found that there were positively charged particles within the nucleus, which he dubbed protons. He assumed that there were both neutral and positive particles in the nucleus, and the existence of those neutral particles, called neutrons, were confirmed by the English physicist James Chadwick in 1932. With this new model, protons and neutrons were about the same weight, with protons having a positive charge and neutrons having no charge. With this, everything seemed complete. We understood the atom perfectly. Except, of course, that wasn't the case. In fact, it was about to get a lot more complicated. Researchers began to find a whole host of particles inside the nucleus, which were discovered by colliding atoms together in a particle accelerator. I'm going to skip a lot of ground here, but there were a bunch of particles that were found to be even smaller than protons and neutrons. These particles became known as elemental particles. These included things such as quarks, leptons, antiquarks, antileptons, bosons, photons, gluons, and neutrinos. And amongst the ones I've listed, there are many different types and flavors. The person who began to make sense of all this was a Caltech physicist by the name of Murray Gell-Mann. He created a model that made sense of everything called the Standard Model. The Standard Model is probably worth its own episode at some point in the future, but suffice it to say, it explained much of how atomic particles were put together. Even the Standard Model, as much as it explained, is still in need of updating as more and more discoveries are being made which don't perfectly fit the model. Our understanding of the atom still isn't complete. Understanding the workings of the atom has been one of the most important projects of humanity. How the atom works is the bedrock underlying every other science, including all of chemistry and all of biology. What started as an exercise in philosophy in ancient India and Greece is still being developed today in the world's largest particle accelerators, 2,600 years from when it started. Everything Everywhere Daily is an Airwave Media podcast. The executive producer is Darcy Adams. The associate producers are Thor, Thomsen, and Peter Bennett. I just wanted to extend a big thank you to everyone who is supporting the show over at patreon.com. I have show merchandise available there, including hoodies, t-shirts, and stickers. Plus, it really just helps me get this show out every single day, including, of course, weekends and holidays. Remember, if you leave a review or send me a boostagram, you too can have it read on the show.